This is AP Chemistry Kinetics Part 2, and these are the 5 topics we're going over today. So integrated rate law is how concentration of a species in the reaction depends on time. So time t is a very important factor in integrated rate laws. In first order integrated rate law, this is how it looks like, and AT represents the concentration at time t, and A0 represents the initial concentration. So natural log AT equals negative KT plus natural log initial concentration. As I just said, time is a very important factor because this integrated rate law is all about how the concentration changes over time. As we went over in the last lecture, this is how the concentration versus time graph looks like, just a smooth line graph. But for integrated rate law, natural log concentration versus time gives a straight line graph. You can simply think of y equals ax plus b graph, and in this case, the a, the slope, would be negative k, the rate constant. So because rate constant has a negative sign, we can see that the natural log concentration values are decreasing over time, but they have the constant slope. And for this unit, you will have to know the temperature affects the rate of the reaction. So at higher temperatures, the molecules would have a higher kinetic energy and they would move faster. So as the reaction proceeds faster, the reactant will decrease over time, but in a faster rate. So the concentration of AB will decrease at a faster rate, so will the natural log AB. So at higher temperatures, the graph would have to look like this, decreasing but at a faster rate. But in colder temperatures, molecules would have less kinetic energy, so the reaction rate would be slower. So natural log AB, or the concentration of AB, would decrease but more slowly. So this is how the graph would look like. And we're moving on to half-life. So half-life is one of the most important concepts in this unit, and you will have to know how to calculate half-life, and you have to know what the half-life exactly means. It is the time it takes for the concentration of a reactant to decrease by half. So if you look at the graph, the half-life represents the time it takes for the concentration of 1.0 to decrease to its half, which is 0.5. And the half-life for the first order reactions stays constant every time. So half-life is 0.693 over the rate constant. And you can calculate the rate constant if you know the half-life, and you can calculate the half-life if you know the rate constant, because they're in an inverse relationship. In this graph, you can see that half-life stays constant. Half-life and rate constant are inversely proportional, which means if half-life is large, then rate constant would be small. And if half-life is small, then rate constant would have to be large, which means that if the rate constant is large, the reaction would be fast, and because the reaction is fast, the time it takes for the reactant to decrease by half would be much faster. Question asks, for a first order reaction, the rate constant was 1.45 over years, and the initial concentration was 5.0 e to the negative 7 molar. It asks, what is the concentration 1 year later? So the T would be 1 year. And you have to bring up the integrated first rate law equation, which is ln AT equals negative KT plus ln A0, which is the initial concentration. And you simply have to plug in the data, which would be negative rate constant 1.45 over years times T, which is 1 year, plus natural log initial concentration, which was 5.0 e to the negative 7. And then, in order to find the concentration at time t 1 year, you have to put all this value into the exponent of e. You just put this into your calculator, and you get negative 15.958657774. You want to keep as many decimal places as possible for the accuracy. For the answer, you get 1.2 e to negative 7 molar. You have the 2 sig figs because the question gave you 2 sig figs here and 3 sig figs here, so you are using the less amount of sig figs. The second question asks, how long will it take for the concentration to drop to 3.0 e to the negative 7 molar? So this is asking for the time, and you have to bring up the equation again. ln AT equals negative KT plus ln initial concentration. You have to plug in the data, except for the time because that is what you're looking for. Natural log of 3.0 e to the negative 7 equals negative rate constant 1.45 over years times t plus natural log of initial concentration. And you have to solve for t, the time. You move this to the left side. Equals negative 1.45 over years, the time. And you solve for t, which is 0.35 years. You are having 2 sig figs here as well. Next, we move on to the second order integrated, and this is how the equation looks like. 1 over the concentration at t equals KT plus 1 over the initial concentration. This is the differential rate law graph, concentration versus time, which gives you the steep, smooth line graph. And this is the graph for integrated rate law for second order reactions, which gives you a positive line graph. And you might wonder why the y values are increasing over time. And that is because the reactants, the concentration A, would have to decrease over time. But in this case, the y values represent the 1 over the concentration, which would have to increase instead of decreasing. You cannot forget about the temperature. At higher temperatures, the molecules would have higher kinetic energy, and they would move faster. So reactants, the concentration of A, would have to decrease, but at a faster rate. In this case, the y values represent 1 over the reactants, so 1 over the reactants would have to increase, but at a faster rate. So the graph would have to look like this, increasing, but at a faster rate. At colder temperatures, the molecules would have lower kinetic energy, so the reactants concentration of A would have to decrease, but at a slower rate. Therefore, 1 over reactants would have to increase, but at a slower rate. Graph would look like this, increasing at a slower rate. The last topic we are going over today is the zero-order integrated rate law. It gives the equation of AT equals negative KT plus the initial concentration. It gives a straight negative line graph. This is the zero-order differential. They do not look any different because reactants have to decrease over time. And this is the end of the video, and thank you for watching.